Mhm. So we went through some topics already, and there are those quizzes that you should do. Yes? And then we have the exam after next week, not next week, but then the week after. Yes. Oh, there's even more people coming. Wow. Place to be. Yes. Hello. I'm gonna do one more thing. So we are in the proportion and percentage. You can do those. I have put there a couple of more exercises, but I still didn't actually update it. I will update it now. So you can, while I'm doing this, you can already do those exercises, whatever you need to do from there. And I will soon give a little bit of information on that. On that. Those there. So we were doing these exercises, and you can find them from the model anyway, but I will do a little update on those now. That's right. Change that. Open. Have you already been doing the quizzes on this topic? Not yet.
The quizzes were way easier than the questions, though. Like much easier. The quizzes are much easier than the questions.
Than the questions here, than these exercises that we are doing. Yes, because they are from this course, like they are very, very basic. Yes, yeah. Because they are from this course that some people do to get into this school, actually.
Yeah.
Oh yeah, now we have. Yeah. I don't know if it's possible to do anything with those windows now.
Yeah, I was thinking I can just permanent that on the window.
Because I would need some kind of a remote to be able to put the.
Well, is that what that's?
There's a remote. Yes. Wow. Let's see.
I don't know if it's
Wow. This works.
Ask everybody. Okay, you can block the sunlight. A little sunlight we have.
But the other one doesn't. The one doesn't go. So okay. this is because sometimes, yeah, these things. But it's fun. It's nice with these modern applications because you have many everythings, but then if they work or if they don't.
Yeah, they always work in, but never in random.
Yes, they are super nice, but like, well, we got, yes, but this one. In some classrooms that they don't work at all. Yes. So now I have here these, and I put there the couple of more proportion as physical phenomenon. 4 exercises more, and that's it. There's quite a lot of exercises on this topic, and we didn't even go to the percentage yet. So it might be that we won't do the system of equations before the exam, but let's see how it goes. Okay. So then I have this presentation. I think it's okay. So I did this because I was talking about one physics topic again in this context. That sounds proper English. So we are still in the direct and inverse proportionality topic. And we already went through this, but there's just okay, 2 variables are directly proportional if they increase or decrease together at the same time. The ratio is constant, and this is, you get this at the straight line. So if you solve the y from this equation, of course you get the k times x, and the k is the slope. If x doubles, y doubles, if x halves, y halves. This is something that you already know. There's this equation for the graph, straight line through the origin. For example, this distance and time when you have a constant speed, or wages and hours worked. Maybe that's how it works in the real life as well. Or Hooke's law, spring extension. What do I say? What does this mean? Yes.
Distance versus times.
Versus, yeah, versus is the word. Spring extension versus force applied. Good. But maybe you look at that in the physics. We won't look at that here at all. And then if you have the inverse proportionality, 2 variables are inversely proportional if one increases while other decreases. So their product is constant. And then if you solve the y from here, then you end up dividing this kind of factor here with the x. So if x doubles, y becomes a half, of course. That was the inverse proportionality. And you actually get this kind of hyperbola as a graph. And then we have the Boyle's law, pressure versus volume of gas at the constant temperature. And then there's versus, yes, light intensity versus distance squared. Well, there's, these are like useful in many, and many equations are actually like this in physics. So yes, direct both increase and decrease together, and inverse one increases, the other decreases. Oh, here is the, or inverse, well, okay, let's go to the Yes, the physics applications. So if you have the Boyle's law, it's the relationship between pressure and volume of a fixed amount of gas at constant temperature. So you have gas in some container and you pressurize it, or it does maybe some kind of work even there. But this is something that then you will further here in the thermodynamics. Here we just do a couple of simple calculations of this. Yes. If volume decreases, pressure increases, and vice versa, inverse relationship. So it's basically like this. You have pressure 1 times volume 1 is pressure 2 times volume 2. So you have the gas in the initial pressure and volume, and then the final pressure and volume. And here, for example, if the initial pressure was 100 kilopascals and volume was 2 liters, and suddenly it's pushed down to 1 liter, then the pressure is 200 kilopascals. This has to remain the multiplication of these two variables has to remain constant. Yes, okay. So it's you know, the calculations are really simple. And here you would have, this is from our physics book. This, so if you apply more force, and then here you have, for example, 1 liter volume. Yes, connection unstable. And the pressure is 100 kilopascals, and then you put it to half it. Of course, this has to, the pressure has to rise to 200, or if you add the volume here, then the pressure goes to half, basically. And it makes this kind of, this is called the hyperbola. How do you pronounce that? Hyperbola. Okay. And then you can, of course, have another kind of, you can, but we just, maybe we recognize, okay, this is an inverse relationship here. This is, it looks like this. Okay, so that was the Boyle's law. Then you have a Charles law, how the volume of a fixed amount of gas changes when the temperature changes. And there you have the direct proportionality. So you have again a certain amount of gas. It's the same amount all the time. And here it's this division that stays constant. Okay, so let's look at this. Volume 1 divided by temperature 1 is volume 2 divided by temperature 2. So if you heat up the gas, the volume, it will, you know, those molecules will start bouncing more, and it needs more volume. Volume and temperature are directly proportional when pressure is constant. So this is the direct proportionality of this. And here you change the temperature or the volume, but the pressure remains constant. And here is some curves for, here is the pressure 1, pressure 2, pressure 3. It's always a straight line. Everyday examples, for example, hot air balloons, heating the air inside increases volume, lifting the balloon. Yes. So this is how you get into the air with the, you know, you heat the air and it gets basically lighter and you go up. Or car tires in cold weather, temperature drops and you have lower tire pressure. Okay, but we don't, that's just the physical background, and now we just do some simple calculations with these equations. We don't need to know that much, then that's in the, mainly in the physics. So if you, here, if you have gas at the volume of 2 liters at 20, so what is the volume at 80? And you just apply the Charles's law here. So it was the volume divided by the temperature, or temperature divided by the volume, that the ratio stays constant. We just do a couple of, this is not actually, it should show the equations still here, but okay. And here, what you need to do in this kind of thermodynamical calculations, one thing, maybe you talk with Jaakko about this as well, that you have to put the temperature from Celsius to Kelvins, so that they actually apply, so you get the correct answer, yeah? Okay, so Boyle's law was inverse proportionality, so the product, the multiplication stays constant, and Charles's law, direct proportionality, and this division is constant. Okay, yes. Summary, combined gas law. So then you could have all of these variables there. And this is actually where all of these come from. So you have this kind of, have you seen this before? Is it from the, have you seen it in the physics? No. So it's pressure times volume divided by temperature. In one circumstance, it's pressure times volume divided by the temperature on this other atmosphere, basically. But you always have the amount of the substance that is there, the gas. It's always the same, constant, and one of these variables you can put constant. So if the pressure is constant, then this goes to the Charles law. Or if the temperature is constant, then it goes to the Boyle's law. Does it make any sense? Okay, so I can take a look at this. Maybe, so there's many laws and laws, you still can, but we don't even need to know basically the names. But there were some people who were researching this earlier, at the 1800s, or, and then they figured out this kind of a dependency. And then there's always their names in it. Yes, that's how it works. Boyle's law, Charles's law, and then there would be even some more people researching this, and they came to this kind of a conclusion. When to use and whatever. Yeah, here is even but you have to always convert the temperature. If there's a temperature there in the calculation, you have to put it to Kelvin. Whatever. Weather values, hard fires. That's it. So then there was in this proportionality, sorry about this, doesn't look very fancy, but it says here proportion as physical phenomenon. So you can use either Boyle's law or Charles's law. And here you have the inverse proportionality, and here the direct. Those were our actual topics. And then there is a couple of calculations of these. So let's go through these calculations now. If you have, for example, the volume of sauna, and you start heating this, you put on the, what is it called? What do you put on when you put on the sauna?
Rock. I don't know what it's called. Yeah, where the rocks are and stuff.
Yeah, that thing. What is it in English? Yeah.
Stove.
Oh.
Stove. Maybe stove. Who has been in sauna? Has everybody been in sauna? Not everybody, yeah. But here people, you will soon figure it out why people want to go to sauna when the winter comes. That's the only warm place. You heat up the sauna and you have a certain volume there, but of course you have the certain volume of the air in the sauna and it's in constant pressure. What would be the constant pressure in sauna or anywhere you go?
Air pressure.
Yeah, air pressure. Yeah. So it exists in the air pressure like we all do here. All the living creatures on the earth have the certain air pressure on top of us, yes? So then you have a constant pressure, but the air expands. So you can just really easily calculate with this kind of a dependency, what is the new volume of the air. This is something that we are supposed to do now. Does this seem like understandable?
Yeah.
You know what you should do. Okay, let's start doing this. So this was a little physical sidetrack of this topic because those calculations there that I had were a bit like they don't maybe have so much to do with your field, but this has at least to do with your actual studies. Yes. Good. And the calculations are actually really simple, just using those couple of simple equations. That equation is actually here in the heat and thermodynamics. This basic. Have you ever seen this equation? Equation of states for ideal gases. Is this equation familiar to anybody of any of you? For who is this, who has ever seen this equation before? At least one of you? Yes. So this is something that you will be using a lot in the thermodynamic. Here you have the, so somebody figured out that pressure times volume is equal to the number of moles times this kind of a molar gas constant times temperature in kelvins. And this is, of course, for a fixed amount of gas. So we are in a closed container. We don't put anything more there. And then we can figure out with certain variables, these, of course, these letters always mean something. And in the simple calculations, you always have all of them given except one, and then you solve one. Yes. So all these letters mean some value. And then you put the value there and then you solve the one that you don't know. But from this being constant, you get this equation and these laws that we have there here, the Boyle's and Charles's law. So, or actually maybe Boyle and Charles, and then the other dudes did this research separately during some decades, and then this was combined to this kind of consideration. So this is actually what we are using here. Does this seem complicated or okay?
Yeah, for me, that seemed a bit.
It's a bit like, yes, but this is just like something that I introduced to you now that you will then see later on, and you will actually calculate. Now we just calculate a couple of examples, like just how you use this kind of equations. That's it. We don't need to know now much about it.
Yeah.
Where do you think that this kind of calculations could be useful?
Hydraulic.
Yeah, or for example, when you make have to check the correct term. Heat engines. What is a heat engine? Car motor?
Yeah.
Well, if it's
Or-
not electrical
Yeah.
motor, yes. You are in the mechanical engineering, so maybe that's something that's of your concern at some point, or any type of heat engines. Most of our electricity is produced with that as well.
What's it?
Also, nuclear power
Yeah.
is to do with the heat engine,
Okay.
because you make the electricity with the
Oh, you're spinning.
you spin this
Turbine.
turbine with the you get a vapor.
Yeah.
Water vapor, expanding. And that this is how it works. So it's also has this kind of considerations there, yes. Cool. So I'm writing this here, how do you actually, based from this kind of a consideration or dependency, how you would end into this kind of laws? Do you see what I'm doing here? How that would happen? Does that seem clear?
And temperatures. Why is it constant?
Yeah, so you consider this kind of person, the processes of heat engines. You think in many ways in this kind of a simplified manners, you think one step at a time. So you think that one thing is constant and the otherwise you modify. And this is many times where you also gain to, you try to gain in your real processes, even if you don't get there, because that might be the most efficient way of doing it. So you try to maybe reach this kind of steps there. But this is like some kind of like, these are simplified calculations basically. So we think, for example, here, if we come from this kind of equation, and we think that, okay, now we are doing something in a constant temperature. In this process, something's happening in the constant temperature. So then we get this equation to look like this. So the T, here we have T1 and T2. Of course, in this, we think that they are separate temperatures. But if the temperature is constant, of course, T1 is T2, which we can just mark with T. If we mark something with T and we put it under here, so T1 and T2 were both T, we get rid of it if we just multiply with it. The equation from the both sides, yes. And we come to this. Does this seem clear? Yes. And it's the same also here then. If we have the pressure constant, so then the P1 is P2, so that's a P, only a P. So then if we come from here, from this relationship there, I'll just put it first immediately there as a P. So it's not, it's the same. Same for both. Here. Continue that line. So how do we get rid of it now? What would you do to this kind of equation to get rid of the P from both sides?
Right.
Yes. We just divide it with the P and then, you know, P divided by P is 1. Yeah, but the 1 you don't mark there as any multiplier. Yes. Good. So we get into this Charles's law. And here we have the direct proportionality. That sounds like a long word. I hope. This is how you say it in English, isn't it? Or it makes sense. Does it make sense? Yes. Okay. Seem to be actually lacking the calculator. Okay, but anyhow. This would be, of course, the temperature one, yes. And the other one would be the volume one.
Yeah.
Yeah. Temperature 2 and volume 2. And then you just calculate it with the simple dependence. That you have. Or you can mark it like this as well. Whatever you, however you prefer. Now I have a wrong. These are difficult for me to keep. The correct, what is that called? Index? Or is it called index or?
I don't remember now. Yeah, maybe, I don't remember.
Yeah, I don't know either. For this. So it seems to be the ratio of those temperatures. Understand? If I can do it with my other calculator. Oh, yours looks like this. You don't have the fancy button that I do. No, the one where you can put on the same line. Over,
Oh.
you don't have that, yes. So, but here, it doesn't matter. You get something from there. Something like this. Of course, this is again cubic meters, and then there it's asked how much air has left the sauna. So then, of course, it's the what's the word? So you have to, of course, how much air left the sauna. Because the sauna volume is still constant.
Yeah.
But of course, it can go, the air can go out of the sauna. So it's not like if the sauna volume is constant, it's like a constant, it's like a constant volume in some container. It's not like any container. Yeah, so then you just diminish 7 point whatever. Minus 6, yeah? And this would be cubic meter. So you get 1 point. I can round it to 1.3. Yeah? That's a good rounding for this. Does this make sense?
So what, like? I don't understand if there's, I don't know, it makes me feel like I'm gonna be stupid, but. Why is it going up? Why is it a positive number instead of a negative?
You mean this? Or what?
Yeah, like, the question is, how much air left the sun? So then. Oh, okay, no, no. I wanted it, in my mind, it should be a negative number, because it's, like there's sauna,
Uh-huh.
the air in sauna. And then it's leaving,
Yeah.
but if it's positive, then that feels like air would be added. Does that make?
Ah, okay. Yes. Yeah. But it's basically you just have the fixed
Yeah, yeah,
certain amount of some gas
yeah,
and you heated it up.
yeah.
So it expanded.
Also, yeah,
The air expanded, now it's air.
yeah,
And then so it requires, of course, a bigger volume
yeah,
that we got from here. So we had it was at first it was 6 and now we got a bit more than 7
yeah,
cubic meters because we heated it up and it expanded. This is how the heat engines work. You heat
Yeah.
up some stuff and it expands and then it gives you some motion or what you're looking for. Yeah. So now the sauna, because sauna is not any container, it just went out.
yeah,
But this is what happens to the air inside your house as well, yeah?
yeah. So,
Yeah, you heat it up and some of the heat you already lose because it expands and then it goes out. So you heat up your house, but you can't do anything with the air going out and taking your energy there as well. Yeah?
okay.
Mm-hmm.
I just have this, I guess, I'm so fixed on it being like, like a glass of water.
Uh-huh.
The water goes away. Doesn't mean there's less water. But I don't know why I'm getting stuck in that.
Okay. Okay, but there were a couple of more calculations. So now you have the eight. Stop. Mhm. So here, of course, you have again 1 and 2, yeah. And now it looks like the Boyle's law would be here, the one that we use, yes. Do you find these exercises, who finds these exercises easy? You, yes. They are pretty easy. It's a simple equation. We have some kind of background here, but these calculations are simple. Yes. Good. So we had this dependency here. And it looks like we want to solve this. So then you divide it all with the pressure, or then you can just write it like this as well. So that it seems like there is the ratio of the pressures now. And then you have there some weird unit, the MPa. Do you know what it means MPa?
Megapascal?
Yes, megapascal, yes. It sounds like NBA or something. Very funny. So it means that you would multiply the SI unit PA, this is Pascal, with 10 in the power of 6, yes. Or 6 zeros after the, you would move this dot 6 times, basically. Yes, okay. So I have the ratio. And what is this 0.1013 MPa? What does this number mean? Well, it says it already there. It's the atmospheric pressure. It's the air pressure that we all can feel in our everyday lives. So obviously here I don't have to do any modifications with the units. Why would that be? That I don't have to put this into the sort of SE units. Because, well, they both have the MPa, and then also it cancels out, yes? Yes.
Yeah.
Cancels out. So it doesn't make any, it's, if it would be different, if there would be some kilopascals and megapascals, for example, or pascals and megapascals, then I would have to consider, but here, now I don't. No, maybe 41.6, 5. How much is the cubic decimeter? 1 liter.
Oh,
Yeah, it's like your milk carton. Yeah.
yeah.
So you had some amount of oxygen gas, and then you take some out, but you take it to a different pressure. What is this 1 bar now?
I think 100,000 Pascal is equal to 1 bar.
Yes. And this is the atmospheric pressure as well. Yes, we can also express it as 1 bar, but then that would be like we have had been rounding from this number. Yes. So bar this is something that's really widely used, even if it's not like any SE unit or anything, like it's just times 10 in the power of 5. Yes, the bar. And I guess it's something that's been invented so that you could talk about the atmospheric pressure as number 1. Yes, it makes it simple, as a simple concept. Okay. So I would have to know how much left, how much gas left this cylinder. I don't know what is the simplest way of thinking about this, but. If you think it through the equation, for example. It was this. Key to volume 2, or that it's constant. So if the constant amount is, it has to be constant in the cylinder. So then this, for example, the amount that left. Amount taken out in this way, considered this way. If we have pressure times volume. So it would be 50. Oh, first. In that order. 1 bar times 50. So I get something a bit like weird here. Maybe I put that unit first. Now this unit looks really weird. This is what went out. Amount of it. Amount. And amount. In cylinder. Would be, if I think it like this. So I would have a bit more there, but it's just, even the volume is less, but the pressure is of course a lot greater. So I have a lot more. Yeah.
1,000
And then now I have again bar times. It feels a bit weird. But this is how much, considering like this, I took out, yes. So at first, amount in cylinder. Afterwards. Then of course would be, you take this out of this. For example, like this. Minus 50. And this unit was a bit weird. So you get 50. Maybe this can be done some other way as well. Okay, but the pressure anyhow, now you know what's left, so, yes. Um, So this was constant, this, mm,
I have one question. The volume is like of a gas cylinder is 40 decimeter, but the used amount is more than the the health.
the more than the 40, yes. But it's in a different pressure. So, it was pressurized in this cylinder, in 110 bars, so this is like 110 times our atmospheric pressure. What was in the cylinder, the pressure. So, when you take it out of the cylinder, you took a little bit out of the cylinder. And you took it, of course, to our air pressure, what is here, because, well, not of course, but that's what happened, it leaked or something, you took it out, or you inhaled it or whatever. Maybe you were diving, I don't know how this works. And then you were, but if you're diving, then you have more than the air pressure, okay. You're not diving, you need the oxygen anyway. And then, because you have the water pressure there as well, yes, okay. Yeah, so it expanded to the pressure of the atmospheric pressure. Yes, it was not pressurized anymore, so it could take as much volume as it needs in the one bar. So that's why in this, I don't know how much volume it took, but here it takes 50 cubic decimeters, yes. Okay, so then, for the pressure in the container, pressure in the cylinder, in the cylinder afterwards. Would be that, that amount. Oops. Divided by the constant volume, yeah? No, I don't like this. This was the bars. Somehow I don't like this solution now, but maybe this could be done some other way. Yeah, well, okay, but this is not our main topic anyway. This is. There's one more. This is easy. This is again the same, isn't it? Length of yeah, air pressure remains constant, so it's exactly the same as the one that we calculated before. Here. We calculated before the sauna. Leaves the classroom, this is exactly the same, yes? Yeah. Would that be a good question for the exam?
Number 10.
Yes,
Um, yeah,
it's a good question for exam, isn't it?
I guess it depends if I can get it right then, yeah.
So we just need the volume, yeah. Did you like the topic this time?
Yeah, I think it's cool, but I just, I don't know very much about pressure. Like,
Soon you'll know more. What can you do if you're studying here?
yeah,
I don't know.
yeah. It's just hard, like with 110 bar. I don't know, is that a lot? Or, I don't know, like,
I have
Yeah.
to think about another kind of solution to that. But I also did this like yesterday, maybe. I was trying to find out some simple calculations for this dependent. Anyhow, you're able to calculate this on your own, the last one, yes? I don't have to go through it here. So you can do this kind of calculations easily if I just tell you what any number means. Nothing like complicated, but just like give some numbers and say that one changed and it follows this equation.
Yeah.
Can you?
I think the maths part is quite,
It's really easy,
Yeah.
yes,
it's maybe more the physics part of it, or like,
yes.
if you just give me the numbers, that is.
If I just give the numbers, you can just put them into the equation and solve one, because it's really, really simple. I think it's anyway nice to know that you actually use these things somewhere rather than just calculate something that doesn't have any connection to anything
Yeah,
that you actually do here.
I enjoy these. Like I enjoy seeing how it gets used. Rather than just like here's some words to the maths.
Yeah. Yeah, so it's nice to find some kind of connections to the actual topics. So I don't promise that will happen every time though. Sometimes we might just calculate whatever number. Okay, good. But now you know something about thermodynamics already as well. next week we have to continue with the percentage. Calculations, so simple percentage calculations, it's not like we have to do those a lot, because everybody has done them at some point, yes. But just that, like we usually, and for sure there, well, there was like only one calculation from some, it's of course.
One thing, see with advantages, we have to learn that, there's little formulas to. If something. Oh, sorry.
Yes. Oh, what are you solving? Yours is solving the system. Okay, so what's wrong there?
Okay. Method and acceptable.
Yeah,
And
and then you,
I don't know. I would say. Like, I calculate as X.
and then. Uh. It's still the same. And then. Here. And then. Oh. I can't really see that.
Okay, so I think is that.
Where was it from? Was it from the stack exercise?
Yes.
A quiz.
Yeah. The stack in.
Were you thinking that there is something wrong with the calculation there?
I don't think. I think it is the impact.
Okay, which one would that be then?
I don't know how it will not take the substitution. The. Two. Equations become one to. That's.
System of two equations. Here you think that there's something wrong. Here it's five exercises.
The line is really long by the time you sit down, it's gonna be almost gone.
Oh, so I practice exercises.
And which one of these would it be?
I'm doing the quiz, the first one. Huh?
Or maybe it shuffles. It doesn't shuffle. There's not shuffle on,
Okay.
I think. So it should be this first one,
Yeah.
first of these.
First.
So is it looking true? Thank you, because this is also really good if you find, hey, by the way, I have your calculator. It's really good. Okay,
Thank you.
thank you. If you find some, like mistake.
Yeah. Let's
If
try.
if there is a mistake, I should look it through.
Okay.
Thank you.
No problem.
Yeah, because this is like,
But it may also be, I just don't know how it wants me to. Like express the syntax.
okay, so maybe it's with the express. Okay,
Yeah.
but I have to look through this first one of these, because yeah, there's not even the shuffle on, so it should be the same
Okay,
exercise.
okay. Well,
Depending on.
What's the right angle triangle? Like, I don't know if it gets caught now, but you know, did I talking to him about, I think it was a part you're not clear of, or like, where to start? You know what I mean?
Do you mean like the ones, the more complicated ones, the physics ones? But we are not gonna do something like that in the exam anyway. That's just an application.
Yeah,
But even the beginning part was confusing to me, it wasn't very familiar. Like,
The physics part. Right.
and then, started,
so like, when you use, but, when to use sine?
yeah. it was-
When you do use sin and when to use cosine. Yeah, yeah. So that's something, yes. That's the main part, main thing to learn from that. Have you been doing the quizzes on that part?
Was because I went to practice with the PDF.
Yes, and the PDF is more difficult than the quizzes. The quizzes are always simple, and with that knowledge also, you already get through this course. So if you know as much as is in the quizzes, to get through this course, that's enough. The quizzes are simple, yeah. But then we just do maybe a little bit more like content. Maybe for the following topics, for example, the next topic, system of equations, we won't have any applications because I have none. And nobody could figure out any who I asked. So for sure we are, for example, learning that for some reasons that you will do later on where you use it, but or these power rules and absolute value. Most probably, maybe we'll just keep into this more simple content. Do you think that would be a good idea, or?
Like, I like seeing, like, some of the stuff, like linear equations, I don't remember any of that. Or I don't remember doing it still, but it's nice to, where it goes to,
Yeah,
but. Like, I don't know, like, I quite enjoy seeing how it's used, as opposed to just doing the maths for it, but.
yeah. And maybe I will also, I don't know, because there's maybe enough content already in this, but
Yeah. I know that always stands out. It's like like opposite of the right hand.
so you should try to do the quiz.
Yeah, so if I can do the quizzes, then that's enough to do.
I think that's enough of this topic. Yes. But then of some other topics, maybe not. So, but what to pick from this topic, because then you will use these right triangles later in the applications of the other courses. But you don't have to do those applications. You don't have to get them yet here, just to be able to use the right triangle, what it actually means. Yeah. Maybe we could also concentrate a bit more on the sort of like simple content. But we will also do some kind of reset or whatever before the exam.
Yeah.
So we could do just something maybe really simple or.
Like, what, I guess, I don't know what would be easier for you, like, because for me, how when it comes to the linear equation was the most difficult part for me so far, but I don't know, it's the very, basics of it, you know, if I can see it as a, if I can see it looking similar to y equals mx plus something,
Yes,
then it's easy, but I always find it more hard when I just have numbers and have to plug it in. I guess I just have to practice. You know?
yeah,
Yeah,
and maybe there could be more of this kind of simple exercises to practice. Because here we also have, you did these ones, did they help you with that? Or are these
which one?
the linear equations quizzes?
Yeah, actually the quiz was way much easier than I thought. It would be, you know, the actual, like I did all the PDF stuff. And then the quiz was very easy.
Super easy. So afterwards you find it super easy, don't you? Yes. But we can't do like this is the basis, you know, and basically this should sort of be enough to pass the course. But you still have to do the exams and you'll get some points for sure enough to pass them. But of course we have to like have a little bit more there, yes. Even if it's just the basic math skills that we are trying to learn here. It would be good that there would be a lot of like exercises that one could actually thank you. I will to solve. I'm still recording this for on the line, but that one could practice with if one needs with solutions, because here isn't that much of the content. There's the quizzes and then there is something a bit more challenging with the solution, but that's it. But I don't have that kind of like old material from anywhere.
I don't know how people learn now, you know, like I've seen the Henry. Yeah. You know, when I done the triangles, I got taught it, you know, like suck at that hole. And anytime I say that to people, like they look so confused, so